In today's lesson, we are going to be looking at Pascal's triangle, specifically at the notation. So you may have heard of Pascal's triangle before, you may have seen it. It is kind of an interesting math concept, and we're going to be looking at it because it does involve combinations. Before we get into that, though, let's review a little bit of what we've already covered so far in this unit. So the first question, a hand in the card game Bridge consists of 13 of 52 cards. How many different bridge hands are there? So again, because we're talking about hands, order does not matter. So in this case, we have 52 options, and we're choosing 13 of them. So that gives us 6.35 times 10 to the power of 11. So that's how many options there are, or how many 13 card hands there are. You want to order a medium 3-topping pizza. There are 8 toppings available. How many different pizzas can you order if you choose 3 different toppings? Again, we're choosing 3 different toppings. The order doesn't matter. They're all going on the pizza. It's still going to give us the same pizza, regardless of whether we put the pineapple on before the ham or before the hot peppers or something like that. Right? So the order doesn't matter in this case. So we have 8 total toppings. We're choosing 3 of them, which will give us 56. Not 52, 56. So there are 56 different pizzas that we could order. 3, a standard deck of cards. We're using a standard deck of cards. How many 5-card hands will contain at least 1 queen? Now, you could go through and you could look at the direct method. Again, because we're looking at hands, order does not matter, so we should be using combinations. So at least 1 queen. Well, that would be 1 queen and then 4 remaining cards. 2 queens, 3 remaining cards. We'll say 3 random, 4 random. 3 queens, 2 random. 4 queens, 1 random. Can't really do 5 queens because there are no 5 queens in a deck of cards. And here you would go through and you look at, okay, well, how many ways can I choose the queens? Multiply by how many ways can I choose no queens based on how many cards are available, right? Which would basically be the 52 minus 4. So we would have 4 choose something times 48 choose something, depending on which case we looked at, and we'd have to add all the cases up. Now we could do the indirect as well, which would probably be a little bit shorter. It may not necessarily be easier depending on how you understand the question, but it would definitely be shorter. So the indirect looks at the total ways of completing this scenario without any restrictions, just in general, what are we doing? Minus the impossible or the complement. So the opposite of at least 1 queen would be 0 queens. So in total, we're basically selecting or choosing 5 cards. So 15 or 52 choose 5, minus no queens, which would be 48 choose 5. I have 48 cards that aren't queens, choosing 5 of them, and end up with 886,656. Lastly, Massimo's Pizza has 17 different toppings. How many possible combinations of toppings are there? And based on your answer, what are you assuming? Well, if we look at the 17 different toppings, and we're going to assume that cheese is not counting, or cheese is already going to be on the pizza. So that's one assumption we can make. So cheese is already on. You're going to also assume there's no doubles, things like that, no repeats. So no doubles / extra toppings. Maybe say I want extra pepperoni, something like that. So only 1 topping, no extras, no doubles, cheese is already on. How many different possible combinations are there? Well, you could go through and say, well, I have 17 options and I choose 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 all the way through. Or the quicker way, each item has 2 options. It's picked or it's not picked, raised to the power of 17 because there are 17 different items and each one has the 2 options. I do this and I get 1,000 or 131,072. So that's how many ways there are. Now I'm not subtracting 1 because I'm assuming you're allowed only cheese or the null set. So I'm allowed to choose no toppings and just have cheese. Right? I've already been assuming cheese is on there. So I have 131,072 different toppings. If I'm only allowed singles of each, cheese is already on there, and I'm allowed no toppings, basically meaning cheese. So that's how many possible options there are. So now we're going to move into Pascal's triangle. So this is the kind of format of Pascal's triangle, and I want you to go through and fill in the different spots. Right? So take a look at each empty spot in this triangle, and I want you to go through and fill it in. Right? So take some time, think about what we see in this triangle, and see what would I have to do to fill it in. I'm just going to use the magic of technology to quickly fill this in. So my triangle is now filled in. Do we notice any patterns? Well, hopefully if you're able to fill in the table, you would have at least been able to recognize that each spot below is the sum of the 2 previous answers, or the 2 previous spots. So 4 is the sum of 1 and 3. Let's say if we go down to 20, that's the sum of 10 and 10. Over here, let's say 36 is the sum of 28 and 8. Now, are there any patterns that you see in the rows? And if we look at it, this would be considered row 0. So Pascal's triangle starts at zeros. So row 0, row 1, row 2, 3, 4, 5, and so on. So do we see any patterns? Well, you might see a couple. You might see that, well, we're repeating numbers, right? So we see 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So we're seeing a repetition as we go through each row. You could also look at the diagonals, right? Thinking about, well, each diagonal, the first ones are 0, or sorry, are all ones. The next row is 1, 2, 3, 4, 5, and so on. And same with the other one. Right? There are plenty of patterns in Pascal's triangles. So there's a lot of work that's been done as looking at recognizing or trying to identify all of these different patterns. And we're going to focus on just a couple of them. So if I look specifically at the terms in the first row, or row 0, so again, that would be the first one up here. I want to add them up. What is the sum of the terms in row 0? Well, if I look at that, there's only the one shape, so the sum will be 1. What about row 1, the next one? Well, the sum is 2. And the third one, 1 plus 2 plus 1 is 4. The fourth one, row 4, 1, 3, 3, 1 is a sum of 8. And then the next one is a sum of 16. What conclusions can you make about the sum of the terms in the row and the row number? So if we look at the sums, is there a pattern that we see? You could look at the next one, row 6, and take a guess at what the sum might be. Same with row 7. And you might find that when you look at each row, row 0 is 1. That's 2 to the power of 0. The next row, 2 to the power of 1, which is 2. 2 to the power of 3, which is, sorry, I screwed up my numbers on the side. Should be 2, then 3. So 2 to the power of 2, which is 4. 2 to the power of 3, which is 8. 2 to the power of 4, which is 16. So this follows each row is 2 raised to the power of whatever row number it is. So the sum of the elements in row n would be 2 to the power of n. Now, where have we seen that before? Actually, we saw that in the previous lesson, looking at some of the problem solving with combinations. And we saw that the sum of all possible outcomes or possible combinations for selecting a certain number or any number of items was 2 to the power of n. So this Pascal's triangle actually has a lot of connections with combinations. So Pascal's method, again, how the triangle works, basically the terms of Pascal's triangle are generated by adding the two adjacent terms and placing the result immediately below them in the next row. If we want to get technical, the technical terms, the term NR, or row number n and then position r, plus term nr plus 1 is equal to term n plus 1 r plus 1. So again, that's just a very convoluted way, just basically saying adding the two adjacent terms and placing the result below. Now, you can actually use combinations instead. So all these term numbers are actually the same as the combinations of specific objects in choosing a set amount. So we can actually use, instead of t for the term number, we can actually use combinations. N choose r plus n choose r plus 1 equals n plus 1 choose r plus 1. So Pascal's triangle is actually just an application of combinations. And we can actually rewrite Pascal's triangle using the choose notation. That's why when we add the sum of each row, we get all the possible combinations for a certain number of items. So for example, we have the first one, 0 choose 0, then 1 choose 1, or 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Right, so these are again for all the different rows, and it's showing us all the different possible combinations. So for two objects, I can either choose 0, 1, or 2 of them. For 3 objects, I can choose 0, 1, 2, or 3 of them. Right, so in general, I can use the position numbers and figure out the value just by using combinations. Right, so if I want to figure out, say, this value down here, if I want to figure out term in row 5, position 2, that's the same thing as saying 5 choose 2, which would give us 10. So we would find that at position 5, or at row 5, position 2, we would have a value of 10. Now again, the one thing to keep in mind when we're dealing with the rows and position numbers, Pascal's triangle always starts with 0. So row 0, position 0. We can kind of see that a little bit more clearly when we see the combination notation. So we're just going to be looking specifically at the kind of combination notation, or the notation of Pascal's triangle and some of the characteristics of it right now. So just in general, looking at the different positions. So term 5, position 3 plus term 5, position 4 is going to equal what? Now you could use the position or the general notation for Pascal's method or Pascal's triangle, which was T and R plus T and R plus 1 is equal to T n plus 1 R plus 1. So this would work out to, because these are two terms side by side, it's going to equal be row below, so it would be row 6, and position r plus 1, which we have here, or position 4. So this would give us row 6, position 4. Because again, this is Rn and R, and this would be N and R plus 1. The same thing would apply with the combination notation. So I have position 8, or 8 objects, choosing 5 of them, and then position 8, or sorry, row 8, position 6, or 8, choose 6. This is going to give me the next row, which would be 9 objects, or row 9, choose r plus 1, which was 6. So again, it's just using Pascal's method to help us figure out what this would be the same as. Now we can do a little bit of subtraction with this. So 8 choose 4 minus 7 choose 4. Now this one's a little bit tricky, but we want to look specifically at this portion. Right? We want to look at the 8 choose 4 because that's the row below 7 choose 4. So 8 choose 4 would actually be comprised of what? Well, it would be comprised of the sum of the two terms above it, which would be 7 choose 3 plus 7 choose 4, the two terms above it. So then if I subtract 7 choose 4, the only thing left is 7 choose 3. 8 choose 4 minus 7 choose 4 would leave us with 7 choose 3. Again, just kind of working out with the notation. The next one, 100 choose 88 minus 99 choose 87, is again a similar concept. Right? So this 100 choose 88 is below 99 choose 87, or row 99, position 87. 100 choose 88 can actually be broken down into 99 choose 87 plus 99 choose 88. And since I'm subtracting the 1, since I'm subtracting this one in my expression, then that means that this part, the 99 choose 88, is the remainder. So again, this is just looking just looking at some of the notation, looking at Pascal's method and how we kind of can use it to help us find different position numbers. That's all it is. So just kind of very straightforward. What we want to do now is we want to take a look at the diagonals. So let's calculate the sum of the first 4 terms of the diagonal, or of diagonal 2 in Pascal's triangle. So if we look at Pascal's triangle here, again, the diagonals work the same way as the rows. So they work at, this is diagonal 0, so we'll call this D0, D1, D2. So if I want to look at the first 4 terms, so that would be 1, 2, wrong row, 1, 3, 6, and 20. So what would those work out to? Well, 1 plus 3 plus 6 plus 10 equals 20. So the sum of those first 4 terms is equal to 20. Now, where do we see that? Well, actually, we see that right here. We see that in our triangle. So how does that look in terms of let's use some term notation here. So we have term 2, position 3, or sorry, row 2, position 3, plus term at row 4, position 3, plus term at row 5, oh, no, I'm getting that mistaken. My mistake. Sorry, let me repeat that because I'm getting confused again because I'm forgetting that we start at 0. So it's actually the first one, 1, is row 2, position 2. 3 is row 4, position 2. 5 is, or 6 would then be term or row 5, position 2. And then the last one would be row 2, 3, 4, 5. Oh, I missed one. A lot of mistakes here. But again, it just kind of shows a little bit of the complexity in the notation. It is simple. It just can be, it's just easy to get mixed up. We just want to make sure that we're clear. So all of that works out to what? Well, that gives us actually, when we add them all up, that gives us the term at row 6, position 0, 1, 2, 3. So we can kind of see how this kind of pattern works. It's all the term 2, and then it gives us or position 2, and then it gives us position 3 in the next one. So let's calculate the sum of the first 3 terms of diagonal 1 in Pascal's triangle. So in this one, we would have term 1, or row 1, position 1, plus row 2, position 1, plus row 3, position 1. And what would that equal? Well, if we were to look at it, 1, 2, 3, that's the same as saying 1 plus 2 plus 3, which would give us, a little too big there, positions, or we would give us 6, which is the same thing as, if you're looking at our terms and kind of how the patterns go, it would give us the next row, so term 4, position 2, which it does. Or you could say 4, choose 2, because again, we can use that choose notation. So let's try to do that looking at the first 5 terms of the diagonal 5 in Pascal's triangle. So the first 5 terms, so we're going to start with term 5, position 5. We kind of see that row 1, position 1, row 2, position 2. So whatever diagonal we start at, if it's 5, it's going to be row 5, position 5. And it's always going to remain 5 as we go down the rows. So that's the first term plus the second term. So 6, 5, 7, 5, 8, 5, 9, 5, oops, term 10, 5. 5, 6, 7, 8, 9. Oops, one too many. So I have 5 terms starting at 5, 5, then going down a row, but the position number is staying the same. It's just the row number that's changing. And that is going to equal the next row, so 10, but it's going to be position 6. So 1 off of that diagonal. And if we want to calculate this, we can use this term notation and use combination notation instead. So 10 choose 6, which is equal to 210. And if we were to go back, let's just for sake of argument, let's go back to our larger triangle. We look at diagonal 6, so 0, 1, 2, 3, 4, 5, 6. And if we go down the diagonals, 0, 1, 2, 3, 4, 5, 6. If we were to go down the diagonals, so 1, oh, no, 5, sorry, 1, 0, 1, 2, 3, 4, 5. So we're starting at this one. I'm getting my questions mixed up. Starting here, so this position plus this one, 2, 4, 5. And it gives us one that is just off, which is over here, which was the answer that we got. So again, just different ways if we want to try to find specific values within um, Pascal's triangle. So the main thing here, just a little bit of an introduction to it, just to kind of have an understanding of some of the patterns that are involved in Pascal's triangle, a little bit of the connection between the actual values in each row and the diagonals, and how it kind of relates to combination notation, and just how it's basically the same values. We are going to look at, in a future lesson, we're going to look at how we can actually use Pascal's triangle to help us with certain combination questions. But this lesson is just kind of focusing on just a little bit of introducing the patterns, as well as brief connection between between the triangle and combinations.